In computer science, a stack or LIFO is an abstract data type that serves as a collection of elements, with two principal operations: push, which adds an element to the collection, and pop, which removes the last element that was added. The term LIFO stems from the fact that, using these operations, each element popped off a stack in series of pushes and pops is the last element that was pushed into within the sequence. This is equivalent to the requirement that, considered as a linear data structure, or more abstractly a sequential collection, the push and pop operations occur only at one end of the structure, referred to as the top of the stack. A stack may be implemented to have a bounded capacity. If the stack is full and does not contain enough space to accept an entity to be pushed, the stack is then considered to be in an overflow state. The pop operation removes an item from the top of the stack. A pop either reveals previously concealed items or results in an empty stack, but, if the stack is empty, it goes into underflow state, which means no items are present in stack to be removed. A stack is a restricted data structure, because only a small number of operations are performed on it. The nature of the pop and push operations also means that stack elements have a natural order. Elements are removed from the stack in the reverse order to the order of their addition. Therefore, the lower elements are those that have been on the stack the longest. History. The stack was first proposed in 1946, in the computer design of Alan M. Turing as a means of calling and returning from subroutines. Subroutines had already been implemented in Konrad Zuse's Z4 in 1945. Klaus Samuelson and Friedrich L. Bauer of Technical University Munich proposed the idea in 1955 and filed a patent in 1957. The same concept was developed, independently, by the Australian Charles Leonard Hamblin in the first half of 1957. Stacks are often described by analogy to a spring-loaded stack of plates in a cafeteria. Clean plates are placed on top of the stack, pushing down any already there. When a plate is removed from the stack, the one below it pops up to become the new top. Non-essential operations. In many implementations, a stack has more operations than push and pop. An example is top of stack, or peek, which observes the topmost element without removing it from the stack. Since this can be done with a pop and a push with the same data, it is not essential. An underflow condition can occur in the stack top operation if the stack is empty, the same as pop. Also, implementations often have a function which just returns whether the stack is empty. Software stacks. Implementation. In most high-level languages, a stack can be easily implemented either through an array or a linked list. What identifies the data structure as a stack in either case is not the implementation but the interface. The user is only allowed to pop or push items onto the array or linked list, with few other helper operations. The following will demonstrate both implementations, using pseudocode. An array can be used to implement a stack, as follows. The first element is the bottom, resulting in array 0 being the first element pushed onto the stack and the last element popped off. The program must keep track of the size of the stack using a variable top that records the number of items pushed so far, therefore pointing to the place in the array where the next element is to be inserted. Thus, the stack itself can be effectively implemented as a three-element structure. Structure stack. Max size. Integer top. Integer items. Array of item. Procedure initialize. stk.items. New array of size items. Initially empty. stk.maxsize. Size. stk.top 0. The push operation adds an element and increments the top index. After checking for overflow. Procedure push. If stk.top equals stk.maxsize, report overflow error, else stk.items stk.top x stk.top stk.top +1. Similarly, pop decrements the top index after checking for underflow, and return the item that was previously the top one. Procedure pop. If stk.top equals 0, report underflow error, else stk.top -1 are stk.items stk.top. Using a dynamic array, it is possible to implement a stack that can grow or shrink as much as needed. The size of the stack is simply the size of the dynamic array, which is a very efficient implementation of a stack, since adding items to or removing items from the end of a dynamic array requires amortized time. Linked list. Another option for implementing stacks is to use a singly linked list. A stack is then a pointer to the head of the list, with perhaps a counter to keep track of the size of the list. Structure or frame. Data, item. Next, frame or nil. Structure: stack, head, frame or nil. Size, integer. Procedure: initialize, stk, head nil, stk.size 0. Pushing and popping items happens at the head of the list. Overflow is not possible in this implementation. Procedure: push, new head, new frame, new head, data x new head. Next, stk, head, stk, head, new head, stk.size, stk.size +1. Procedure pop. If stk, head equals nil, report underflow error, rstk, head, data stk, head, stk.head. Next, stk.size, stk.size 1. Return. Are stacks and programming languages. Some languages, like Perl, Lisp and Python, do not call for stack implementations, since push and pop functions are available for any list. All Forth-like languages are also designed around language-defined stacks that are directly visible to and manipulated by the programmer. The following is an example of manipulating a stack in Common Lisp. Greater than, set the variable stack greater than, get top element. Should modify the stack a greater than stack. Check the value of stack greater than. Push a new top onto the stack. C++'s standard template library provides a stack templated class which is restricted to only push-pop operations. Java's library contains a stack class that is a specialization of vector. PHP has an small stack class. Hardware stacks. A common use of stacks at the architecture level is as a means of allocating and accessing memory. Basic architecture of a stack. A typical stack is an area of computer memory with a fixed origin and a variable size. Initially, the size of the stack is 0. A stack pointer, usually in the form of a hardware register, points to the most recently referenced location on the stack. When the stack has a size of 0, the stack pointer points to the origin of the stack. The two operations applicable to all stacks are a push operation, in which a data item is placed at the location pointed to by the stack pointer, and the address in the stack pointer is adjusted by the size of the data item. A pop or pull operation. A data item at the current location pointed to by the stack pointer is removed, and the stack pointer is adjusted by the size of the data item. There are many variations on the basic principle of stack operations. Every stack has a fixed location in memory at which it begins. Stack pointers may point to the origin of a stack or to a limited range of addresses either above or below the origin. However, the stack pointer cannot cross the origin of the stack. In other words, if the origin of the stack is at address 1000 and the stack grows downwards, the stack pointer must never be incremented beyond 1000. If a pop operation on the stack causes the stack pointer to move past the origin of the stack, a stack underflow occurs. If a push operation causes the stack pointer to increment or decrement beyond the maximum extent of the stack, a stack overflow occurs. Some environments that rely heavily on stacks may provide additional operations, for example, duplicate. The top item is popped, and then pushed again, so that an additional copy of the former top item is now on top, with the original below it. Peek. The topmost item is inspected, but the stack pointer is not changed, and the stack size does not change. This is also called top operation in many articles. Swap or exchange. The two topmost items on the stack exchange places. Rotate. The n topmost items are moved on the stack in a rotating fashion. For example, if n equals 3, items 1, 2, and 3 on the stack are moved to positions 2, 3, and 1 on the stack, respectively. Many variants of this operation are possible, with the most common being called left rotate and right rotate. Stacks are often visualized growing from the bottom up. They may also be visualized growing from left to right, so that topmost becomes rightmost, or even growing from top to bottom. The important feature is that the bottom of the stack is in a fixed position. The illustration in this section is an example of a top-to-bottom growth visualization. The top is the stack bottom, since the stack top is where items are pushed or popped from. A right rotate will move the first element to the third position, the second to the first and the third to the second. Here are two equivalent visualizations of this process. Apple banana banana equals right rotate greater than cucumber cucumber apple banana equals left rotate greater than cucumber apple banana. A stack is usually represented in computers by a block of memory cells, with the bottom at a fixed location, and the stack pointer holding the address of the current top cell in the stack. The top and bottom terminology are used irrespective of whether the stack actually grows towards lower memory addresses or towards higher memory addresses. Pushing an item onto the stack adjusts the stack pointer by the size of the item, pointing it to the next cell, and copies the new top item to the stack area. Depending again on the exact implementation, at the end of a push operation, the stack pointer may point to the next unused location in the stack, or it may point to the topmost item in the stack. If the stack points to the current topmost item, the stack pointer will be updated before a new item is pushed onto the stack. If it points to the next available location in the stack, it will be updated after the new item is pushed onto the stack. Popping the stack is simply the inverse of pushing. The topmost item in the stack is removed and the stack pointer is updated, in the opposite order of that used in the push operation. Hardware supports stack in main memory. Many CPU families, including the x86, Z80, and 6502, have a dedicated register reserved for use as stack pointers and special push and pop instructions that manipulate this specific register, conserving opcode space. Some processors, like the PDP-11 and the 68000, also have special addressing modes for implementation of stacks, typically with a semi-dedicated stack pointer as well. However, in most processors, several different registers may be used as additional stack pointers as needed. Stack in registers or dedicated memory. The x87 floating point architecture is an example of a set of registers organized as a stack where direct access to individual registers is also possible. As with stack-based machines in general, having the top of stack as an implicit argument allows for a small machine code footprint with a good usage of bus bandwidth and code caches. But it also prevents some types of optimizations possible on processors permitting random access to the register file for all operands. A stack structure also makes superscalar implementations with register renaming somewhat more complex to implement, although it is still feasible, as exemplified by modern x87 implementations. Sun Spark, AMD AM29000, and Intel i960 are all examples of architectures using register windows within a register stack as another strategy to avoid the use of slow main memory for function arguments and return values. There are also a number of small microprocessors that implements a stack directly in hardware, and some microcontrollers have a fixed depth stack that is not directly accessible. Examples are the PIC microcontrollers, the Computer Cowboys MUP21, the Harris RTX line, and the Novix NC4016. Many stack-based microprocessors were used to implement the programming language Forth at the microcode level. Stacks were also used as a basis of a number of mainframes and mini-computers. Such machines were called stack machines, the most famous being the Burroughs B5000. Applications: expression evaluation and syntax parsing. Calculators employing reverse Polish notation use a stack structure to hold values. Expressions can be represented in prefix, postfix or infix notations, and conversion from one form to another may be accomplished using a stack. Many compilers use a stack for parsing the syntax of expressions, program blocks, etc., before translating into low-level code. Most programming languages are context-free languages, allowing them to be parsed with stack-based machines. Backtracking. Another important application of stacks is backtracking. Consider a simple example of finding the correct path in a maze. There are a series of points, from the starting point to the destination. We start from one point. To reach the final destination, there are several paths. Suppose we choose a random path. After following a certain path, we realize that the path we have chosen is wrong. So we need to find a way by which we can return to the beginning of that path. This can be done with the use of stacks. With the help of stacks, we remember the point where we have reached. This is done by pushing that point into the stack. In case we end up on the wrong path, we can pop the last point from the stack and thus return to the last point and continue our quest to find the right path. This is called backtracking. Runtime memory management. A number of programming languages are stack-oriented, meaning they define most basic operations as taking their arguments from the stack and placing any return values back on the stack. For example, PostScript has a return stack and an operand stack, and also has a graphics state stack and a dictionary stack. Many virtual machines are also stack-oriented, including the P-code machine and the Java virtual machine. Almost all calling conventions, the ways in which subroutines receive their parameters and return results, use a special stack to hold information about procedure, function calling and nesting in order to switch to the context of the called function and restore to the caller function when the calling finishes. The functions follow a runtime protocol between caller and callee to save arguments and return value on the stack. Stacks are an important way of supporting nested or recursive function calls. This type of stack is used implicitly by the compiler to support call and return statements and is not manipulated directly by the programmer. Some programming languages use the stack to store data that is local to a procedure. Space for a local data items is allocated from the stack when the procedure is entered, and is deallocated when the procedure exits. The C programming language is typically implemented in this way. Using the same stack for both data and procedure calls has important security implications of which a programmer must be aware in order to avoid introducing serious security bugs into a program. Security. Some computing environments use stacks in ways that may make them vulnerable to security breaches and attacks. Programmers working in such environments must take special care to avoid the pitfalls of these implementations. For example, some programming languages use a common stack to store both data local to a called procedure and the linking information that allows the procedure to return to its caller. This means that the program moves data into and out of the same stack that contains critical return addresses for the procedure calls. If data is moved to the wrong location on the stack, or an oversized data item is moved to a stack location that is not large enough to contain it, return information for procedure calls may be corrupted, causing the program to fail. Malicious parties may attempt a stack smashing attack that takes advantage of this type of implementation by providing oversized data input to a program that does not check the length of input. Such a program may copy the data in its entirety to a location on the stack, and in so doing it may change the return addresses for procedures that have called it. An attacker can experiment to find a specific type of data that can be provided to such a program such that the return address of the current procedure is reset to point to an area within the stack itself, which in turn contains instructions that carry out unauthorized operations. This type of attack is a variation on the buffer overflow attack and is an extremely frequent source of security breaches in software, mainly because some of the most popular compilers use a shared stack for both data and procedure calls, and do not verify the length of data items. Frequently, programmers do not write code to verify the size of data items, either. And when an oversized or undersized data item is copied to the stack, a security breach may occur.